his physics class.
No, yeah, I just want to watch it.
I would still vote for you.
It's really... My clocker.
Should be singing. Singing? Their music? Oh. Somebody sing.
Do you think there ever be a gay president?
Not my business.
Okay.
You're supposed to sing.
I'm supposed to sing? No, I'm not singing. Nobody wants that.
Can somebody make up with a theme song?
Yeah, I never thought they'd do it.
Okay. So. What? Huh? Yes.
Really?
I do.
Really?
Yeah.
I don't want
He doesn't like Halloween.
Now they take the Snapchats.
Okay, anyway.
Ergen style.
Okay.
Do you want him as your president? Are we gonna watch
Do I
the?
want you to?
Are we gonna watch the polls tomorrow as they're going up?
But it's the most...
No, I don't care.
It's like running around.
How?
And whether we watch it or not has no bearing on it.
Yes.
So,
Oh,
Right.
that is the most inaccurate statement I've ever
like if we see how they voted Virginia, that's going to impact here.
Yeah.
Yes.
Yes. Virginia's a
Photons
sweet
can
state.
somehow affect. You know. You should know this. You're a physics teacher.
It's called the principle of non-locality.
Oh, that's not.
No, it doesn't.
That's not.
Okay.
That's
Yeah.
what
Oh yeah. So you're
I
saying
like
about
technology for a lot.
That's something.
That's it.
Okay.
What?
Anyway.
Well, no.
I don't understand what
Okay.
just happened.
So here's what we have left. So today being Monday, we've got the introduction to angular motion today. Tomorrow we have angular momentum review on Wednesday, and then the test over all things motion and with momentum, both linear and angular, is going to be on Thursday.
I'm gonna be going
Okay.
Tuesday and Thursday.
Oh, sucks for you. Okay, that's why God made YouTube. Okay, all right. So here's what we've got. So today we need to talk about what happens with angular motion, and then from that we'll get into angular momentum tomorrow. So here's the deal. So if I take this wheel, and this is why angular motion gets a little bit more complicated, because I can have the wheel moving where I have linear motion, but I also have angular motion where this thing is spinning around. I can just have angular motion where the wheel is spinning, but yet it's not moving. But I can also have the wheel moving without any spinning. So I can have pure angular motion, I can have linear and angular motion, or I can just have angular motion without the wheel moving at all. So we have to be able to account for all three things. Now, the other thing that happens is that when things spin, they do weird things. So if I take this wheel and hold up one side like this, and I drop it, and it just goes doink, okay? Literally, just goes doink. But if I take that wheel and get it spinning, then it'll stay up.
That's honestly kind of cool.
And process around like this, okay? And as it slows down, it gets more and more
Oh, it's like a top, huh?
The thing's got some high momentum.
So it is, okay? And this has to deal with this concept of angular momentum. So there's a whole bunch of things that happen when things begin to spin. You get into what's known as angular momentum. We'll get into that tomorrow. So today we kind of just need to lay out the...
You open that up upside down.
Okay? So today we just need to lay out the groundwork. Now, here's the other thing that's different about angular motion. So basically, all the linear motion physicists have taken all the good variables of x, distance, a for acceleration, all this stuff. So the angular motion guys were pretty much left with the Greek alphabet. So we need to do a quick introduction into the Greek alphabet. There's going to be three variables that we're going to use. Theta,
Pi.
omega.
Is that a W?
No, it's like a
It's an omega.
alpha.
It's a horseshoe. Two of them.
No.
Now, let's just get this straight now, or you're going to think you're the first person in civilization to realize this, and you're going to say it, and you think you're clever, and you're not. It looks like a butt. Get over it.
I was thinking they look like boobs. I mean, you think that.
Anyway, so let's just get this out of the way right now. It's the butt. It's not. Okay, it's omega. So basically, it's theta butt fish, if you want to think of it that way. Okay. Now, the other thing that happens when you talk about angular motion is that you have to be able to describe how far the wheel moves, but without necessarily talking about how far it moves. So when you talk about because like for example, you can talk about this point right here and how far it moves, but that doesn't necessarily mean that the wheel is moving. Okay? So you can have a point on the wheel that's moving without the wheel actually moving. So
it's stationary, but it's moving.
Radians, I'd say.
Close.
I'm going to think yes.
You're just going to throw it that way. So here's the
I think
magic
it's torque
go-to
plus
thing.
2.
So one revolution is going to be 2 pi.
Oh my god. I can do this.
Radians. Now, here's the odd thing about radians. It's the only time we'll ever deal with something that's what's known as a dimensionless number. Okay? So we're not going to have like 2 pi radian meters. So if you say, hey, you know, how far did it go? 5. Well, 5 what? 5 meters, 5 centimeters, 5 light years, how far did it go? But if you say 2 pi radians, that's it. Okay, so we're not going to have 2 pi radian meters or 2 pi radian kilometers. Okay, 2 pi radians is just that's it. Okay, it's pure dimensionless number. So this is kind of going to be your go-to idea right here. Now, here's where you've got to be able to cross and understand the relationship between these two things. So theta is going to be how far this thing moves, measured in radians. Omega is basically going to be how fast it spins. So that's going to be in radians per second. And then alpha is going to be your acceleration, which is going to be in radians per second squared. So basically, theta is the same thing as distance measured in meters. Omega is the same thing as velocity, which is in meters per second. Alpha is the same thing as acceleration, which is in meters per second.
Why did they have to change this? Why did they do this?
Because
they're Greek.
Well, no, but here's the deal.
Meters.
It's because I can have this wheel moving. So this point is moving through a certain point, okay? But, so whether this wheel is spinning and not moving, or whether it's moving and spinning, this point is going to move through a certain number of radians. Okay? So that's why you've got to be able to talk about it in a purely circular motion, but then also what happens in a linear motion. So that's why you got to be able to have both of them there.
This must suck if you've never taken pre-calc before. Like this part, you know what I mean? Like
This is the only
pi.
thing you really need to know is that
Radians?
one revolution is 2 pi radians. That's, we're not going to do anything weird with it like trig identity.
Oh, okay.
So this is basically the only thing you need to know.
That's it.
That's it.
From pre-calc. Crossover.
45 degrees. 60 degrees, of course.
Okay, all right.
120 degrees. Oh, maybe I got, no, 120 degrees.
Enough with the trig jeopardy.
All right, how about 75?
We actually did play Trig Jeopardy in Mercy.
I figured that. That's why.
It's
Okay.
Wait, you do that?
Now,
Numerowski?
on the front of that lecture notes and also on your equation sheet, you have 3 crossover equations. And they are D equals R theta, V equals R omega, A equals R alpha. Okay? Now, let me explain why these work and through a simple example. So let's say that I've got this wheel, and let's say that it has a radius of 0.25 meters. Okay? So pretend that you don't know anything about radians, the crossover equations, nothing. We'll get back to those. So here's this wheel. It has a radius of 0.25 meters. So I'm going to start with this piece of purple tape down here at the bottom. And I'm going to roll this wheel across all the way until that purple tape gets back down to the bottom. So what I want to know is how far did the center of this wheel travel during that time? So what's one thing that I could do?
R theta.
I could, but I don't want to do that right
So
now.
your little purple thing is going a full rotation around.
Yes. So so I'm going to pick this point on the tire right here,
Yeah.
right here on the edge. Okay. So I want to know from here to that point gets back, how far did the tire move?
Circumference of the wheel.
Circumference, right? So imagine that I take a piece of string and I wrap it around the wheel, and then I lay that out. So that's how far it would travel in one revolution, right? So, Miss Trigg, how do you find the
I
circumference
don't know
of
if
a
I'm
circle?
Miss Trigg, but isn't it
Hey.
2 pi r? No.
Beautiful.
Yeah.
Yes, yes.
Okay.
Oh,
Okay.
you knew it.
Pi. So the circumference.
Well, I did.
is
Pi on that.
Right? So in this case,
IG. That's circumference.
now, here's the other thing, and this is where physics deviates from math.
I can't do that.
Apparently it's new news to this guy that pi d equals circumference.
Okay. So here's the other thing where this deviates. In math class, they want you to leave it in terms of pi because, oh, it's more precise. And technically, the math people are right. Okay? So this is basically, this is 0.25, which is 1/4. Simplifies down to pi over 2. Okay? So here's the problem. You can't find a meter stick that measures in units of pi. Okay? It doesn't exist. Okay? It does not exist. So the best that you can do is you have to put this as an actual decimal. Is this more precise? Yes. But in the cold hard reality of trying to measure a distance, you can't find something a meter stick marked off in pi over 2. It doesn't exist. So, Mr. Rollins, take pi divided by 2.
Pi divided by 2. 1.57.
1.57 meters. So this wheel is going to travel about 1.5 meters as it makes one complete revolution. Okay? Good with that. So this is one way to do this. If you like this idea, stick with it. It's cool. Now, let's say that you want to go, wow, but Mr. Burkamp, I've got these new equations here. These are cool. Do these work? I don't know. Let's see. So here's the deal. So the tire is going to make one complete revolution. Okay? So if it makes one revolution, Mr. Taylor, how many radians is that?
2 pi.
2 pi radians, right? Okay? So that is my value of theta. That's how far it goes. If it made 2 revolutions, this would be 4 pi. If it made 3 revolutions, it would be 6 pi. So in this one revolution, I traveled through 2 pi radians. So that's my value of theta. So if I want to go with, well, let's try this equation. All right, let's try this equation. So I got 0.25 meters times 2 pi radians, which is the exact same as taking 2 pi r, which is your circumference. So oddly enough, you're also going to get 1.57 meters. Okay? So you can either find the circumference, or you can use theta times r. Now,
Theta times r. What's r?
Yeah, he's right.
The radius.
It's 1.57.
thanks. Okay. Now, here's an interesting thing that you need to look at. So here I've got this wheel, and I'm going to have the wheel move through one revolution. Here I've got the tennis ball. I'm going to have it move through one revolution. What did the two have in common? Ellie, what did the two have in common?
They both moved one revolution.
So how many radians did they both move through?
2 pi.
2 pi. So they both move through 2 pi radians, right? But did they travel the same distance? No. Which one's obviously going to travel a greater distance? The wheel is, because it has a much bigger radius. So when you look at the linear distance that something's going to travel, if something's making one revolution, it doesn't make any difference if it's this wheel, if it's the tennis ball, if it's the Earth spinning on its axis, if it's the Milky Way galaxy moving around the black hole at the center. It doesn't make any difference. If you make one revolution, no matter what the size is, you're going to move through 2 pi radians. It doesn't make any difference. But what does change?
The radius.
But so as the radius gets bigger, the distance traveled gets
bigger.
So it's a direct relationship. So if I double the radius, I'm going to double the linear distance that it travels. Now, here's the other odd thing that happens. So if you look at this wheel spinning, which moves through more radians in one revolution? The point closer to the axle or the point further out? Or are they the same?
Which one?
They're the same. So no matter where I am on this wheel, whether I'm here, whether I'm out there, it's going to make one revolution. So you have to begin to focus on what's a factor and what's not a factor. So the number of radians that it moves through is not dependent upon the radius. It's only dependent upon how many revolutions it moves through. Okay? The linear distance that it's going to travel is dependent upon the radius. Okay? Got that? Fantastic. All right. Now, let's say, for the sake of argument, that I'm going to make this wheel spin at 2 revolutions per second. So first off, is this frequency or is this period? Frequency. Why?
Period is 1 in how many seconds?
Yeah, so this is 2 revolutions per second. So this is an event per unit of time. Okay? So we got this. Now, same tire, radius of 0.25 meters. Okay? Cool with this. Radius is 0.25 meters. So what I want to know is, and it's going to be the same thing, and you'll see why this works. So I either want to know how fast a point is moving on the edge of the wheel, or I want to know how fast the wheel itself is moving down the road, because it's the same thing. Okay? So I got 2 revolutions per second. So let's go old school. Okay? Let's go old school. So if I'm making 2 revolutions per second, how far did I travel in each revolution with a radius of 0.25 meters? How far did I travel? Well, 1 revolution is equal to the circumference, right? Which is 2 pi r, which is going to be 0.25, 2 pi times 0.25 meters, right? Which is going to get me pi over 2 meters, right? That's how far I'm going to travel in each revolution. So if I'm making 2 revolutions per second, Brooklyn, how far am I going to travel? So pi over 2 times those pi's in honor of Thanksgiving gives you what? Huh? Don't make this difficult. I got pi over 2 times 2. Yeah. So I got pi meters, otherwise known as 3.14 meters. All right? True? Everybody cool with this? So I went in 1 second, right? So therefore I'm traveling 3.14 meters per second. Okay? So in this situation, because I'm traveling pi meters in 1 second, because I'm making 2 revolutions, so that means that this thing is traveling 3.14 meters per second. So there's 2 ways to approach this answer, and you have to understand what this means. It either means the edge of this wheel is traveling at 3.14 meters per second. So in other words, if I'm holding this wheel stationary like this, and it's not moving, and I'm just having it spin at 2 revolutions per second, that means a point out on the edge of the tire if you could sit there with a little speed gun and shoot a radar gun at it, a point out there on the edge of the tire is going to read 3.14 meters per second. Sometimes it's called tangential velocity, sometimes it's called linear velocity. So when you get this number in meters per second, it's how fast a point is moving on the edge of the tire. It also means if the wheel is moving, that's how fast the center mass of the wheel is moving down the road. Okay? That's what that means. So there's two things. It's either how fast the point on the edge is moving or how fast the wheel itself is moving. Yes?
So if it's 2 revolutions per second and 1 revolution equals 2 pi r. Okay. Oh, never mind. I got it. I
Good.
thought like since it's 1 revolution equals 2 pi r, if there's 2 revolutions it should be 4 pi r.
It is. But R is 0.25. So 4 times 0.25 is 1.
Yeah. That's just not how it's
You're always right.
No, believe me. Just, I've like.
That's
Okay,
some sorcery.
Okay.
So if there's 4 pi r.
It's 4 pi
It
r
is
times
4 pi r.
0.25.
No, if there's 4 revolutions a second.
And the math's different.
So
Times it by. That's irrelevant in this.
Yeah, it is. Okay, but now, here's an interesting thing.
I don't understand this.
Shut up.
I swear.
Yes,
wait.
he does.
Hold on. No.
So if it's 4 pi r, or if it's 4 revolutions a second, it'd be 2 pi.
Yes.
Yep, I got it.
Huh?
Then it would be
I feel like this is just
2
confusing.
8. Yep.
meters per second.
No.
Because you're spinning twice as fast, so you're going to be moving twice as
Yep.
fast.
Crazy.
Insane. Okay. Now, here's the deal. So I got this thing spinning. So is a point closest to the wheel, right here, close to the hub, is that going to be moving at the same linear velocity as a point out here on the edge?
Yeah.
No.
Why?
There's
There's more
radiance.
distance.
Okay? Are they both? Is any point going to take the same amount of time to make 1 revolution?
Yeah.
Yeah, it's a solid spinning wheel. So no matter where I am, it's going to take the same amount of time. So imagine this is like a marching band, okay? Where you've got a marching band and everybody's going to march around in a circle in a straight line. Everybody's going to take the same amount of time to complete that line, right? But who's got to travel faster?
One on the outside.
Why?
Because they have a longer distance.
To
Radius.
travel in the
Same speed, time.
same amount of time, right? Yeah. Because if they're moving at the same speed as the people on the inside,
Doesn't work.
the
You have a
people on
really
the
bad
inside are
marching
gonna
band.
laugh. Okay? So, as you go farther and farther out, the angular velocity in radians per second stays the same. The linear or tangential velocity increases. Now, this is a situation where you've used this equation. If you look at V equals R omega. So let's approach it from this side, where V equals R omega. So I've got a radius of 0.25 meters. Okay, that's pretty simple. So write that down. Now, omega. What units does omega have to be in? Radians per... What'd you say? What does omega have to be in? Radians per second, right? Omega is going to be in radians per second. So here's the deal. I got 2 revolutions per 1 second. So I want to get rid of the revolutions. And I got 2 pi radians. It isn't 2 pi r. It isn't like a radius. This is just 2 pi radians. So if I take 2 times 2 pi, I get 4 pi. So this is 4 pi radians per second. Okay? Now, here's the deal where these radians are a dimensionless number. So when I multiply meters by radians per second, don't write this answer as meter radians per second. The radians are dimensionless. Okay? So if I take 0.25 times 4 pi, oddly enough, I get
Meters per second?
pi meters per second, or 3.14 meters per second. Okay?
Oh.
Now, listen. So every time you've driven your car, you've used this equation. And you're going, no, I haven't. I've never seen this equation before in my life. Yes, you have. And here's the reason why. So here's a short lesson in auto mechanics. So here's your engine. It transmits power to your drive wheels through your differential. Okay? So here's your tires. So at some point, there is a sensor that picks up how fast some component is moving inside your car. So this sensor, probably in your transmission, is saying, oh, okay, this particular piece of equipment is spinning at so many radians per second. Okay? Then the engineer said, okay, based upon this size tire, that means that car is going to be traveling at a certain linear velocity. Okay? So it says, all right, this piece is spinning at 5 revolutions per second, 10 pi radians per second. This size tire, you're going down the road at a certain speed. This is what your speedometer is showing, 40 miles per hour.
It's kind of cool.
Okay? Wow. Now, let's say, though, you're a teenager and you're in your rebel phase. Okay? And you go, I'm going to break the law. Okay? I'm going to be stupid and get a bunch of speeding tickets.
Dude,
okay?
social norms.
So
Across the train track.
So your mom and dad and the insurance company are about to kill you because you keep getting speeding tickets, but yet you're not bright enough to go, wow, maybe I should just drive the speed limit, then I don't have to worry about it. But you want to maintain this illusion of being a rebel because you're through your rebel phase. So here's what you can do. Take your tires and put on little, like tires that you would see like on a little riding lawnmower. Okay? So now you've got these small little tires on there. Why? So, no, here's the reason why.
Oh, because
now
he's got a point.
Okay?
So it seems like you're speeding, but
oh,
really you're not.
Exactly. So you can be in the car and still look cool to your little punk friends. Go, look, I'm breaking the law. I'm driving 40 and a 30. But in reality, you're driving 30 miles an hour. So, because your wheels go like this.
Make that noise.
No. But you're not going very fast because the wheels have such a small radius. Now, listen to me, guys. This notoriously happens to you. So you go the other extreme and you go, I want to be cool. I want to put big tires on my truck. Okay? Right? So now you put oversized tires on your So you put oversized tires on your little Toyota pickup with a 4-cylinder, okay? So if you put oversized tires on there, what's going to happen?
You're going to drive slower.
No.
You're going to drive super fast.
You're actually going to be going faster than what your speedometer says.
So you have to drive slower.
Yeah, so your speedometer says you're going 40, but you've got these big oversized tires on there, so you might be going 45. So then the cop pulls you over and goes, son, you're speeding. And you go, no, officer, I was driving the speed limit. And he goes, son, haven't you ever learned that vehicles are omega? And if you say, no, I will testify in court and show you this video that says, oh, Skippy was taught this assignment, or Scott taught this equation.
Why would you do that?
You like us better than the cops?
No, because you lied and said you didn't know the equation.
Why?
So,
You lied.
Snitch is dying in court.
Chill.
you really do need to just mellow out just a little bit. It's a Monday.
That's my rebel phase.
I'm trying. I'm trying.
Shut up, Mom.
Okay, so got this.
Shut up, Mom, you're ugly. I've never said that to my mom.
Oh, so help me if you did.
You honestly deserve to get beat if you
Yes.
call your mom ugly.
Okay. All right.
Papa ain't gonna
Now,
be happy
here's the
about
last
that.
equation.
That's some
that
Jake
A equals R alpha. So oddly enough, this is dependent upon a radius. This is going to be the linear acceleration of your car. So if you know that your car is accelerating at like 5 meters per second squared, which is pretty easy to measure, angular acceleration is pretty tough to measure on like on a spinning wheel. So if you know your linear acceleration and you know the radius of your tires, then you can calculate your angular acceleration that way. So here's what you want to look at. D equals R theta.
Agreed.
V equals R omega. A equals R alpha. What are they all dependent upon? Radius. As the radius gets bigger, if this side stays constant, what happens to all of these values?
They increase.
They increase. Okay? That's it. Boom. There you go.
Simple.
Now, if you look at Newton's laws, it's basically the same idea of what happens in angular motion as happens in linear motion. So this wheel was at rest. And guess what? The wheel is going to remain at rest until
I can apply an outside force.
yeah, I apply an outside force. Now, once I get it spinning, guess what?
It's going to keep spinning until acted upon by an outside force.
Yes, I apply an outside force. Voila. Now, if I apply a little bit of force, I get
A little.
bit of acceleration. If I apply a bigger force, I get a bigger acceleration. Okay? So in that regard, that's kind of the same idea. Now, on those lecture notes, I've also given you like these comparison equations where you have that equation where it's v squared equals v naught squared plus 2ax.
Weird.
So basically, this is just everything you've done already.
So basically, wherever there's a v, you put an omega. Wherever there's an wherever there's an a, you put an alpha. Wherever there's an x, you put theta. So you just rewrite this as basically omega squared equals omega naught squared plus 2 alpha theta. If you have a velocity time graph, guess what? We're going to have an omega time graph. If this velocity time graph is linear, what does it mean?
That means you got yourself a
Constant velocity.
Constant velocity. If you have a horizontal line here, it means the wheel is spinning at a constant velocity. If this thing is going up, what's it doing?
accelerating.
It's speeding up, right? Because you're going away from zero. If it's coming down like that, you're
Accelerating.
and slowing down. Okay? So basically, wherever you have VT, you can have omega. If this area here represents displacement that's measured in meters, this area would represent displacement measured in, no, theta is the variable.
Radians.
Measured in radians. Okay? Measured in radians. Okay? All right, so stop that for a second. Stand up, stretch.
Now we're back.
The last big thing for the day, and that's torque. Now, torque itself is a very simple concept. It's force times radius. Sit. Boom. So when you look at torque, if you're French, it's torque. Really not. Usually represented by the Greek letter tau. Okay? Because if you use uppercase T, then it looks like period. So let's just talk units. So what units is the force going to be measured in? Newtons. Radius is going to be measured in?
Radians, maybe? Meters?
No,
Meters.
Okay, well you're just using radians. Use it.
Not for radius. So if I multiply these together, oddly enough, I get Newton meters. Okay? Now, if you're in the English system, this torque is usually measured in what we call foot-pounds, because you've got a radius measured in feet, and you have a force measured in pounds. So if you've ever watched like Dodge or Chevy truck commercials, they're talking about, oh, this is the truck with the largest amount of torque. And they'll say, oh, it's 400 foot-pounds of torque. So the foot-pounds of torque comes from this equation right here. Okay, or if you ever work on an engine, you're going to have to a lot of times tighten bolts to a certain torque, and it'll say, hey, tighten it to 80 foot-pounds or whatever that measurement is. Now, So this is a situation where you have an intuitive understanding of this equation. I just have to make sure that you know what you're doing. So here I've got a deal that.
I gizmo.
Can you see that? Mm-hmm. Okay. So let's say that I take a 50-gram mass and I put it out here on the edge. Okay. Now, if I take a 200-gram mass and put it out here on the edge, what's going to happen?
Look at the 200-gram mass.
Oh, why?
It has more.
Gravity.
Gravity is part of it.
There's more force acting on that side than the other. Yeah. Huh?
There is.
Because of force times radius.
Oh, because it's force times radius. So, is the radius the same for both of them?
Yes.
This has more
Force.
Therefore, this side is creating more torque.
More force
Okay?
than gravity.
So you can look at this in terms of not only net force, but you can look at it in terms of net torque. So when you talk about torque, especially spinning about like a fixed axis in the middle, you talk about like clockwise torque, which once it makes it go this way, and then you have counterclockwise torque, which makes it go this way. Now, is there a way that I could balance this out?
Adding more
Decrease
weight
the
to the
radius
side.
on that side.
I can either add more weight to this side, but let's say I'm out of weight.
Decrease the radius on that side.
Split.
Gravity
This is
storm.
why we're done.
Gravity check.
Gravity check. It still works. So if I move it in here, yeah. I move it way in here. Woo. Okay. So there's going to be a point.
Nope, 9.
Wow.
Oh, yeah.
That surprised me.
I'm going to think of a really simple equation that hasn't been invented yet.
Like F times R?
Like F times R, that's pretty simple.
Yeah, that is pretty simple. So here's the deal. So in this situation, the two torques are the same, right? So you can create the same torque, but torque is a product of two things. So you either change the radius or you change the force. So if I have a large force acting over a small distance, that's the same as a small force acting over a larger distance. Now, here's where you've used torque every day of your life without knowing it. So I come over here and I want to open up the door. Do I have to apply a torque and put that phone in there?
Oh, little hand.
So I go to open up the door. I can push one of two places. I can either push here on the edge, or I can push right here by the hinges. Which one will require more torque to open up the door?
Inside.
Closer.
The inside.
Which one will require more torque?
Both of them had the same.
The one
It's the same amount of torque.
Oh, God.
Why?
Okay.
The radius is different.
I didn't say anything.
Okay?
Oh,
Because
Because
it's
it
the
takes
same
the
distance,
torque.
right?
But if I push right beside the hinges, I'm going to have a very small
Radius.
radius, so that's going to require a
Really big force.
really big force. So I can open it here, but you got to push really, really hard. Okay? Or I can push out here with a much bigger radius and apply a lot less force. Now, if you really wanted to get aggressive, hold a 2x4 on it, okay, and have that 2x4 extend out for about 10 feet. So then you got a huge radius, so then you would have to apply just a little bit. Okay? So this is why there's nothing magic about putting the handle out here. We put the handle out here because it makes it easier to open up the door. We could put the handle right here. Okay, we could.
So weird.
But then you'd be like,
all that extra
okay,
space
and then
on
you
the
just
side.
push out
Yes.
the edge anymore.
It just doesn't make
even
sense.
if you look at, if you look at cabinets, okay, if it's the same idea, we could put the handles for the cabinet right here.
That'd be confusing.
But like, would it make sense though?
Physics just like makes this make sense.
But I'm telling you, you could put them out. You could put
Why
them
don't you
there.
do that? You're a physics teacher, like, that just makes
Yeah.
sense to have them right next
No, it makes sense to have them here. Because if I've got
No,
them
because it
here,
just makes them like,
Just do it, just to be you.
You would have a reason for doing it, because then you could put up a sign that says like.
Look at this, half-times are its work.
I might do that. Just like one.
Yeah, just one of the
Just
Just flip it.
okay. I will give that consideration. Okay. All right.
Somebody just stepped out of bed.
So now, if you've ever been like on a teeter-totter, teeter-totter is basically an example of torque. Okay. So if I'm on one side and Ellie's on the other side, and if we're both equal distance apart, bad things are going to happen, right? So if I want to balance out, I'd have to move in much closer to create the same amount of torque that Ellie does.
Wow, what a discriminate kind of playground toy. The fat people can't play with this. What a just bunch of, what a crock of,
It's
you know freaking what.
okay. All right. So stop that. Let me hand out these. Oh. All right. So let me kind of get you started on problem number 1, just to make sure everybody starts off on the same page. So here's the idea. What's the only time you can calculate velocity using distance traveled divided by time? There's only one specific circumstance. Constant velocity. So just like you can only calculate omega by taking theta over time if it's moving at a constant velocity. If a wheel is speeding up or slowing down, I can't do this. So here's what I want to look at. I want to find the angular velocity in radians per second of all 3 hands on a clock. So we're going to start this together, make sure everybody's on the same page. So if you look at the hour hand, which right now is pointing at just before the 1. So when it gets back to the 1, how many radians has it moved through? 2 pi. So on the hour hand, I'm going to use omega equals theta over time because the hour hand is moving at a constant velocity. So I'm going to have 2 pi radians. Now, here's the question. How long does it take for that to get back to the 1?
3,600 seconds.
3,600 seconds.
Get that. 360. I doubted myself.
It's 3,600 times 24. What is that?
No.
3,652 times.
Okay, right now the little hand is
12.
pointing
43200. 43200.
Okay,
Oh,
hold on.
not an hour.
What?
A full day
No.
to get back.
No.
What are we talking?
Okay.
12 hours.
Okay, look. Kendra,
What?
little Mickey's small arm is pointing towards the 1.
Okay.
It's the little.
It's gonna take 12 hours to get back to the 1.
Yes.
Which that times 3,600 seconds
Yes.
equals your. Yep. Okay.
So here's what I want. I'm going to take 2 pi and going to divide that by 12 hours, change it into seconds. I want the answer with 3 significant digits in scientific notation.
3 sig figs.
Now, let's talk about the minute hand. Right now, the minute hand is just beyond the 9. How long is that going to take to get back?
3,600.
3,600
Seconds.
Why?
Because that's how many seconds.
Because it takes an hour, right? Okay. Now, the second hand, 60 seconds. So which of those 3 is going to have the largest angular velocity?
The second.
The second hand is. Because that's going to take the smallest amount of time to move through 1 revolution. Now, did I give you the radius of the clock in problem number 1? No. Why?
We don't need it.
Don't need it.
Don't need it.
Okay, I didn't tell you that the second hand was red either. Okay,
Do you want?
it's not relevant.
Do you want it an exact pi?
Okay.
So
James, somebody tell James how I want the answer.
But like
3 sig figs in scientific notation.
Thank you.
That was cool.
Okay. Now, here's the deal. Think about this. I've got this clock up here on the wall Got a watch on my wrist. Then you look at Big Ben in downtown London. If you're looking at the second hand of all three, are all three moving with the exact same angular velocity? Yes. But the linear or tangential velocity is going to be different depending upon the velocity. Keep that in mind. Now, when you get down to question number 10, okay, let me kind of lay out what's going to happen in question number 10. You got George and Joe sitting on a balance beam that's 1.75 meters long. So 1.75 is the length of this thing. So you could put the fulcrum where it balances wherever you want to, but you want to put it where it's going to balance out. So you're going to have two things. You're going to have the torque created by George, and you're going to have the torque created by Joe. What's got to happen to those two torques if they're going to balance?
It'll be equal.
It's going to be equal. So the torque from George has to equal the torque from Joe. George has more mass. So are you going to put the fulcrum closer to George or closer to Joe?
George.
Closer to George. Okay? Because you want these things to balance out. So here's what you want to do. It's a similar technique to what we did when we did the Lagrange problem to the moon. No, it's not a quadratic. Don't flip out. It's nothing near that complicated. But what you want to do is let one distance be x. So how much is left over? No. The total length is 1.75 meters. So if you let one distance be x, the other distance is?
Minus x. Or 1.75 minus x.
Yeah, 1.75 minus x, which is going to be the total length minus x. So let, like, the distance to Joe or the distance to George, I don't care, be x. Then the remaining distance is going to be 1.75 minus x. So those two torques have to balance out. Now, when you get down on this back side, if you get into a problem and you don't know how to do it, and you're going, wow, I got nothing. Think of the problem in terms of linear motion, and then try and work that problem that way. So if you look at like number 18, how many radians will a spinning wheel move if its initial angular velocity is 25 radians per second, and it's accelerated 2 radians per second squared for 5 seconds? And you read that problem and go, oh my God, I don't know what to do. Well, look at it this way. If I said, hey, something is moving at 25 meters per second, and I accelerated at 2 meters per second squared for 5 seconds, how far is it going to go?
So simple.
Yeah, so if you can figure out how to work it in a linear situation, basically all you do is use that exact same process and use an angular approach to it. So it's the exact same equations, you just change it up. So, okay, I'm done. You're on your own.